Alright guys, we back live. Oh, you just have to trust that thing in the top right, or top left, right. Okay. We're doing this problem. Yeah, I don't know what happened. Crashed. Must have. I was literally taking a shit while it crashed, so. Beats me. So find the potential energy, PE, starting position relative to its lowest point. Okay. So when it's here, the rope is 3.5 meters long, but he doesn't want to put the work in. What the fuck do you mean? I'm literally doing it right now. Well, we know that's MGH. We just need to change an H. So, basically this difference here. So let's think about it this way. We have this, where this is 3.5. This is 45. And then we have this, which is 3.5 as well. Never back down, never give up. I'm trying my hardest, Big MT. Trying my hardest. And then we just need the difference between these two. So we need to figure out this length right here, which is going to be the adjacent. So cosine 45 equals adjacent over hypotenuse. So 3.5 cosine 45 is what our A is going to be. 3.5 cosine 45 is 2.47. So we take 3.5 minus that, because that's going to be our difference in height. So our height is going to be equal to 1.025. At least I think. We'll find out. MGH, the mass, 400 newtons. Wait, W is equal to mg, so we just need WH. So 400.025 meters. Which just makes sense because Newton meters are joules. Sine squared plus cosine squared equals 1. Yep, sure does. Anyways, the potential energy. Oh my god, it's so bright. Guys, looks like I'm going into heaven. Oh my god. 400 times 1.025. We have 410 joules as our potential energy. We'll check that right later. Find the speed at its lowest point. Okay. Say we're on B, which is velocity at its lowest point. Well, we'll have to find, it's going to be tangential speed, I'm pretty sure. Bro's ascending. I know I'm ascending, bro. Look how it's so fucking bright. Fuck. It would be tangential, pretty sure. Because if we have our radius, well, PE should equal KE, and it's where potential energy is 0. Where potential energy is 0, kinetic energy is going to be at its highest, which is equal to the potential energy. And what we're solving for is this. So 820 over m square root equals v. Okay, this should be right. What's the mass? We don't know the mass, so W equals mg. 400 over 9.8. I don't like that number. It's 400 over 9.8 equals V. Square root 400 divided by, oh, not 400, 820. 20 divided by 400 over 9.8. Bro, I'm just so ready to play later, to be honest. I'm just so tired of this shit. Final speed of the rope makes 20 degrees with the vertical. Are we fucking serious? Okay, well that's kind of hard. So we have PE plus KE should equal 410. So we know that much. That's no. Yeah. So that's the height. Okay, that's what I'm saying. I know, bro. So we're gonna find potential energy when it's mg change in h plus 1/2 m. You're halfway, gang. I'll be back by the time it's done. Bro, I don't think I'm going for 10 hours. I'll be straight. It's just gonna be like a 10-hour long stream. I'll probably be going, I think I said 7 hours, so I think 7.5, because I'll be going till 8 or 7 because I still have to get dinner. Find the speed, so yeah. So change in h. So we know mg, so we need to find the change in h. So change in h is going to be calculus all over again. We talk calculus is fucking easy, bro. So what we did here was found 3.5 well 3.5 minus 3.5 cosine 20. So that's what we're doing right now. Me watching you do all the work. And I'm explaining it too, like I'm fucking organic chemistry tutor, bro. 3.5 minus 3.5 cosine theta is gonna be our change in h. So this should make sense, honestly. So 400 times whatever this value is. Bro, I've had a rapid decline in viewership. It's unfortunate. Yeah, that's right. So, no, it's not. Let's solve the equation first before we actually do any of this shit. So let's see. So we'd have to take 410 minus mg change in h equals 1/2 mv squared. 810 minus 2 mg change in h over m square root. Okay. 810 minus 2, 400, change in h, which is this 0.211, over mass, which is 400 over 9.8. Hopefully this comes out pretty, because if not, it's because of the crash. Yeah, I know. Yeah, you're right. Still though, nobody's loyal enough to me, except you, I guess. So that divided by 400 divided by 9.8. Oh, okay. I mean, that's not bad. 0.96 meters per second. Let's make sure that that's less than what we got last time. 4.48. Yeah, that makes sense. It's so bright. What the fuck? Okay, let's see. For, what is this? 4? Yeah, 2.4. I even watched on my lunch break. Dedicated fan. 3.99. That, okay, so yeah, we got that right. It's a matter of rounding. 512.5 joules. Well, that would kind of mess up everything else. Is that weird? That's really weird. We would need the right potential energy value in order to get the correct velocity. So if it's 512.5, that's 100 off. It's kind of weird. IDK, I just follow you. Maybe you shouldn't. So I obviously don't know what I'm talking about. 70 kilogram, runs up a flight of stairs, 12 meters high. In 8 seconds. Find the work done against gravity. We aren't given a cosine today, so it's just going to be work equals FD. Force is equal to MA. That's not how it's going to work. Is this also physics 2? No, this is physics 1. Yeah, this is regular physics, bro. F equals... How's F equal MA? Oh. A is gravity. Okay, here we go. Against gravity. So that's A. B. 3.5 hours. I've got physics 2 over the summer. 3.5 hours. Dang. It's tough. So, wait, you took physics 1 and you don't know that this is physics 1? I'm confused, bro. Find the power output? What the fuck? I don't fucking know. Power. W times V. The velocity. How the fuck am I supposed to know the velocity? D over T. I never knew what was going on. IDK, I had an Indian teacher. Those are the ones I know the most. You just can't understand. Power and horsepower. 1 HP equals... Okay. Dang, he's got a lot of horsepower. Makes me think it's not right. $16 horsepower. Okay. Let's see how we did on section 2. Oops, went too far. Oh, fuck, way off. 82. Okay, so that was right. It's whatever I did here that was wrong. But V equals D over T. Power equals the change in work over change in time. Oh, it's force times that, not W. That makes sense. I don't feel like redoing this. We know what it is now. So what are we on now? How many horses is that? About 16.55. Energy conservation with friction and springs. energy conservation. Okay, block on a rough incline. 5 kilogram block starts at the rest of the top of a rough incline. So this is 5 kilograms. Mu k is equal to 0.2. Slides 8 meters down to the bottom. 8 meters. Find the change in potential energy. Well, potential energy will just, the change in potential energy is just going to be the max, because at the end it's going to be 0. Potential energy equals mgh. This is going to be our h, or is 8 going to be our h? I don't know. Yeah, h is height. Find the spring constant. I'll do that next problem. I think it's 400 for the next problem. So sine theta equals opposite. So what we're trying to find over 8 sine 30 equals our h. Sine 34. 4 meters. Okay. I might check this to make sure I don't get anything else wrong. Yeah, we're gonna check to make sure I don't get that wrong. Yep, nice. Good for us. Oops, too far. Okay. B, work done by friction. Work done by friction equals the frictional force times the displacement. It does say cosine theta. Cosine theta. Yes, because friction is going to be at an angle, so that will be important. Force of friction is just going to be mu kn, because we're doing kinetic friction only here. Fk mu kn. N is equal to mg cosine theta. Yeah. Okay, ready? Mu k mg cosine theta times d cosine theta. That's funny. Work done by friction. Friction is going to be equal to 0.2 mg 9.8 cosine 30 times 8 cosine 30. Oh. Okay. Oh, fuck off, dude. 0.2 times 5 times 9.8 times cosine 30 times 8 cosine 30. 58.8. Newtons, joules. Find the speed, velocity at the bottom. So just like that. 196 times 2, what is that? 380, 392? Let's plug it in my calculator to make sure. I'm a genius. Divided by 5 equals V. Square root of that. Let's make sure I'm right. Whoa, buddy. Still got a ways to go. Okay, so we're wrong. I wonder with what. Let's see if I just do mg. $67? Yeah. Oh my fuck, dude. Whatever. Shut up, dude. I wonder why we don't include this cosine here. at work right now? Where do you work, Loki? I didn't know you had JOB. How's this wrong though? How's this wrong? Okay, well, don't care. 3.2. 2.2, 3.2. Okay, spring energy. Against a spring, compressing block is then released on frictionless surface. Okay. So the PE of a spring or U spring 1/2 kx squared, right? Yep. Find the speed of the block when it leaves a spring. Really not very good with this stuff. So if the potential energy is equal to 4.5 when it leaves a spring, it's going to be all kinetic, right? Jeez, bro. I think I'm dead again. What would result in a... What is it? What compression would give the block twice the speed? Okay, so now we kind of have to work backwards. Given that, we can use 1/2. We're just going to use 18. Jesus Christ, dude. Can we chill? Oh, double the compression. Duh. Double the compression, double the speed. That's just how it works, innit? But doesn't hurt to go back through again. Problem 3, pile driver. Okay. So when KE is at its max. Should work. Oh, I never checked my answers for the last one. Okay. Find the average force on the beam. Find the average force the beam exerts on the pile driver. So it's going to be equal to the force that the pile driver drives into that. Force. Total force is going to be MGH. Because the forces are going to be equal. Should be this. I doubt that's going to be right because it says it's a hard problem. And I kind of solved that relatively quickly. What unit are we on? Are we on 3? Yeah. 9.9. Yeah, so I got the right one for that. I just don't know how to do B. Oh well. I want to move on anyway. Impulse. That's the potential energy to start with, right? I have P equals, oh, M, yeah. Okay. Should be easy. We need to solve for F, so, or I, sorry. I could do that in my head, but I don't feel like it. 1.375. For the impulse, if the collision lasts, t equals 1.5. So I equals ft, or the average force, F, which means 1.375 over 2 seconds, 1.5 seconds. See if I can fit C over here. Compared to a ball that is stopped, not reversed. So that means VF equals 0. Impulse of that will be equal to 0. So which impulse is larger when opposite direction? Sweet. 2. Perfectly inelastic collision. A 1,500 kilogram car moving this way at 15 meters per second collides with a 2,000. Okay. Okay. They stick together after the collision. This is the equation for a perfectly inelastic collision. Which I don't think we have on our cheat sheet, but it makes sense. So they have the same final velocity, and then the masses get added, right? One is 1,500. We need to find the VF, so guys, I think I'm cooking actually. If this is what the test is like tomorrow, then I've got it in the bag. I highly doubt it though. Find the kinetic energy lost. So KEI, so we're just gonna do this difference. Using this V and this F here. For this, we just use that first guy. And if this results in 0, then we're probably wrong. Okay. Well, it's a lot lost. what fraction of KE was lost. Would that be changing KE over KE initial? I mean, that's the fraction, but this is a percentage. So, they'll count it. We should. Elastic collision. It's 3 kilograms. V1 equals 8 meters per second. Makes an elastic head-on collision with a 1 kilogram ball at rest. Find the velocities of both balls after the collision. Okay, I understand. Let's see. I'm not quite sure. Approach this one. So the max KE is going to be the kinetic energy of the first guy. $96 joules. It's a max kinetic energy. So, how do I find? How do the change in V's work? Have something like this. Just looks kind of weird. Which we have all the numbers for. That's the V1F. Speed after the collision? Oh. Both balls. Okay. And then... I'm just making sure all this is right. because I've never ever used this equation before, which might be a good thing, it might be a bad thing, who knows. Surely that can't be right, right? One half times, come on, it's 24. Holy shit, this might actually have worked. It's 144 divided by 2, 72. Plus is 96. Holy shit, it worked. That's kind of crazy. I think I peaked. Oh. M1 equals 0, 1. Bed itself. 2 kilogram block. Surface. Width. Mu k equal 2.4. Find the speed of the just after impact. So before kinetic energy has acted on it, I think. So it's simply asking for the it's simply asking for this. Which is going to cross out that, so okay, that should be it. How far the block slides before stopping. So if we have this, we have a force against it, which is a friction force. We have the velocity in this way, 0.5 v is and vf is 0 meters per second. The force of friction going to be? So usually it's mu k and is equal to mg. I think it might just be that, to be honest. D. We don't know the time, we don't know the distance, we don't know the acceleration, so we can't use anything like that. So even if we find, so what we want to do is the work done on the block, but we don't know that, and we can't find that out. We don't know the acceleration though, because we don't know the time. Could do v over t, but we don't know the time. Ugh, I just feel so close. We can't do that. We know that the force of friction is that. What are we gonna do with that though, you know? What if we set it equal to the kinetic energy at the beginning? It's not going to do anything. But if we find that, we can find A, which we can use. Right? Well, force equals MA. Oh. We don't need to find the A. We just need to find the force, which is equal to 1/2 mv squared. So, just this part is equal to the force. Can I set MA equal to 1/2 mv squared? I don't know if I want to do that. I don't know if kinetic energy is equal to the work done. Kinetic energy is a work done over a distance. So F in terms of D. Let's solve for this. This is going to be our coefficient for D. F. There we go. Okay. So what's the distance? For it to become 0, we need 2.26D to be equal to 7.8792. Don't think that's right. We're assuming that the distance is 3.49 meters, which like kind of makes sense, but also I don't fucking know. Let's see. 4.4b. Sweet. Yeah. I just don't think I know how to solve that one, which is okay. Does that work? So the other way around. Holy shit, yo. This might actually work. Dude, we got it right. I just needed to relook at the equation. That's kind of crazy. That's what my calculator gave, but I'm guessing they just did a different rounding thing that I don't do, or that it feels like doing, I guess. To find the energy lost. Well, it starts out this much, so it'd just be the 1/2 mv squared, right? Right? But that was 2.26, and I doubt that that's how much energy was lost, because it said like 400 something, didn't it? I wonder if I solved wrong then. KE is that all the energy lost, because it's going from full to 0. 447.8 joules lost. So let's ask about this. Okay, I'm pretty sure we're done with that section then. It's 5 o'clock. I've got 2 more hours left in me. Let's do it. How you guys doing? Should I make sure that the stream's still going? I'm a little concerned now. I don't know why it quit on me. Yo guys, do you guys like the thumbnail? Does it peak? Oops. Oh, I suppose I can see who's all watching. Carter. Okay. Starts at rest. It's radians per second, I forgot. Reaches an angular velocity. Constant angular acceleration. What does angular acceleration look like again? Let's say. What? With constant angular acceleration in 6 seconds. Oh. 6 seconds. Equals the change in this over t. So this is A. E. Find the total angle rotated in radians. Well, this is just the period. Oh, it's kind of hard to calculate, isn't it? I don't really know. Well, actually, I don't know. times does it go around in a circle? Total angle rotated. Oh, okay. So, okay, so if they went 72 radians and revs is equal to 360 degrees, or so 1 rev equals 2 pi radians. So, how many revs, right? Yeah. Which is 36 over pi. Okay. That was pretty easy, as long as I got it right. A grinding wheel completes 75 revs in 4.5 seconds. Its final angular speed is equal to 120 radians per second. Find the initial. So it's going to be similar to this last equation. We just kind of work backwards. So 75 times 2 pi is going to be our period, I think. That is going to be our change in theta. I think. I'm kind of questioning everything now. So we don't have, so we need Wi, Wf, t, and change in theta. So no angular acceleration. Oh, it's the same one we used this before. We need to solve for Wi. Cool. Okay. Oh, I need to find the angular acceleration. Whoops. Oh, wait. Oh, that's the next problem. Okay. So we can just kind of use what we already have. Whatever's easiest. Okay. Guys, we got it all. We're a professional at rotational kinematics. Unit 6. So we need to find the force of the beam. So force of beam divided by 2 is equal to FL. Is equal force is mg, or weight is equal to mg. Oh, wait, it's just 0. Right. So the torque on this baby is Fr, right? Yep. So force is equal to mg. Where's ma? What am I talking about, dude? Oh, a is g. Yep. Yep. So torque on this. Let's do left guy first. Oh. This is without the person, mind you. So this is the T for both. Okay. So total torque is equal to what? R times F. We don't need to find the torque, we need to find the force. Force is equal to mg. Well, I guess we could have found the torque, but oh, whoops, oh no. Oh guys, the iPad's almost dead, I can't even lie. But what does this have anything to do with the torque? Because the radius isn't measured then. Because I don't have nothing to do with the radius. Like, I know this isn't right, but I don't know what else to do. Just double check to make sure they're wrong. Yeah, I don't really know what to do, I guess. Oh, wait, it's not 2400. I just need 600. Still wrong. Yeah, I don't know how to do it, I don't think. Oh, this is strange. I don't think that's right, but I don't know. I don't know what else to do, I guess. I think I'm just bad with the static equilibrium stuff. So let's move on. I don't think I'm very good with this stuff either. Oh. Well, you know the mass. We know that, and we know the amplitude. I know that much. The angular frequency. What's rotational velocity? I don't know how to do this stuff either. I don't know if I know how to do anything from on. Let's try these. Point force. This is point force is v displaced. The apparent weight of water. I don't know how to find that. I don't know how to find apparent weight. Is weight A? I think it is. And then we need to find the density of the object, which is P. Oh, I don't have that. F equals PA. And so this is what we're trying to solve for here. Right? The apparent weight No, that's pressure. But we don't know the pressure. The only way to calculate pressure is by having the density. So we probably aren't supposed to use this. Oh wait, PV equals nRT. Wait, we don't have nRT. Yeah, we don't have anything like that. Find the apparent weight. Water. We have F. We don't have P. Can't get P. Well, I feel better about this stuff because I feel like I know where to get started. I definitely know I have that one. And the density of the object. Well, if we can get the thing, then we can easily get that. I don't think I know how. We might be wrapping up for the day, to be totally honest. I'm really running out of steam. Floats in water. Yeah, maybe we'll watch some. Maybe watching some videos on these. Yeah, let's do that. I think that'll be good for me. Alright, take this off. Yeah, keep looking close. Okay. I'm gonna go use the restroom. I will be a minute. I'll mute myself.
In this video, we're going to focus on solving tension problems. So in this question, a rope is used to lift a 50-kilogram box with an upward acceleration of 2.3 meters per second squared.
I've been muted this whole
What is
time.
the tension
Great.
in the rope? So let's say this is the box, and the rope is lifting up the box. The force that acts along a rope is the tension force.
Honestly, I'm not even. Oh, I might have just stopped the stream. Honestly, I think as long as I can hammer this down, the heat and the fluid dynamics aren't that bad. They really aren't. There's a lot of equations, but they're not that bad. I'll obviously need to sharpen up, make sure that I'm totally locked. But most of it is pretty self-explanatory. And then just memorizing isothermic, isochloric, etc. Oh.
So how can we calculate this tension force? What can we do? Well, we need to set up a free body diagram. We need to identify all of the forces that are in play. So we have the upward tension force, the downward weight force, and also the net force. Now the net force is in the upward direction because the whole object is being lifted up. So the net force in the y direction, which can also be written this way, is going to be the tension minus the weight force. So it's T minus W. Our goal is to find T. Now, the net force is equal to ma. Since the force is in the y direction, the acceleration is in the y direction. And so we got to add W to the other side. So may plus W is equal to the tension force. And the weight force is simply mg. So if we take out m, the tension force is going to be the mass times g plus the vertical acceleration. So this is the equation that we need. So now let's get the answer for part A. So the tension force is going to be equal to the mass of 50 kilograms times the gravitational acceleration plus the upward acceleration of 2.3 meters per second squared. So 2.3 plus 9.8, that's going to be 9.8 plus 2 is 11.8, and then if you add 0.3 to that, that's going to be 12.1. And then we got to multiply that by 50. So the tension force is 605 newtons. Now, if you want to compare it to the weight force, the weight force is mg. So that's going to be 50 times 9.8, which is 490. So notice that when the rope is used to lift up the object with an upward acceleration, the tension force is greater than the weight force. But now, what if the rope is being used to allow the box to slowly descend? Intuitively, we know that the tension force should be less than the weight force if the box is descending with a downward acceleration. So let's get the answer for part B. So m is 50, g is 9.8, but the acceleration, because it's downward, it's going to be negative 0.75 instead of positive 0.75. So 9.8 minus 0.75, that's 9.05, and then times 50, this is going to be 452.5 newtons. So as you can see, the tension force is less than the weight force when the object is slowly descending with a downward acceleration. Now let's work on this problem. What is the tension in the two ropes in the picture shown below? Now notice that the crate or the box, whatever you want to call it, it's in equilibrium, it's at rest. So therefore, the sum of all forces in the x and in the y direction must add to 0. So when you see a problem like this, you want to break down T1 and T2 into its components. T2 has an x component and a y component. T1 also has an x component. So let's focus on the four negative sides. We can see that sine cosine theta 1 to distinguish these two angles. So for T1, the angle that's associated with it is 60. So T1 cosine 60 is equal to T2 cosine 30. Now cosine 60 in degree mode, that's 0.866. That's 1.732. So T1 is 1.732 times T2. So let's save this equation for later. T1y and T2y. Because the object is at rest, the net force in the y direction is weight T1. We don't know what that is right now. But theta 1 is 60 times 9.930. So we got to solve this using substitution. Anytime you have two variables, you need two equations to find or to solve those two variables. So now this is going to be 588, which is equal to 0.866 times 1.88 divided by 2. So just take, so now 60. Now 519.2 times cosine 60. And that's, which is 400, correct? Is make sure all the forces in the x and the y direction, they add up to 0. Let's focus on the x direction. This one is in the positive x direction, so it's positive 254. These two, 400 y direction, calculate forces we have. So we got the downward weight force. We got T2, which is directed towards the right. We have T1, which has an x component, T1x, and a y component. T1, the object is at rest. T1y is T, so next T. So the downward weight force is 100 times 9. In this lesson, we're going to talk about pressure. Pressure is force divided by area. In physics, the standard unit of pressure is pascals. 1 pascal is 1 newton per square meter. And 1 kilopascal is 1,000 pascals. And 1 atm, or atmospheric pressure, is 101.3 kilopascals. So those are some units that you want to keep in mind. So whenever you exert a force over a given area, that force exerts a pressure throughout that area. So pressure is simply force over area. Now what happens if you increase the area, but use the same force? Let's say if we double the dimensions. Now if you apply the same force over, let's say, a larger area, the pressure is going to be a lot less. Let's say if we apply a force of 100 newtons. The pressure in this example is 100 divided by 1 square meter, so it's 100 pascals. In the second example, the area is 2 times 2, which is 4. So the pressure is now a force of 100 newtons divided by an area of 4 square meters, so it's 25 pascals. So what you need to understand is that if you increase the force applied, the pressure increases. If you increase the area in which that force is applied, the pressure decreases. The pressure is directly related to the force, but inversely related to the area upon which that force is applied. Let's try this problem. A 15-kilogram rectangular block with a length of 70 centimeters and a width of 40 centimeters rests on the table. What pressure does the
I
book
would need
exert
this whole
on the
freaking
table?
time, bro.
So let's say this is the book.
I was saying, I think I just need simple
it's on
harmonic stuff, but that's not an option, looks like, for organic chemistry tutor. I'll look it up after.
Now that book
Or
is going to
later.
exert a weight force on the table. And that force is applied over the area of the book, the bottom area. Now we have a length that's 70 centimeters and a width
I mean,
of
this
40
is easy.
centimeters. And we know that pressure is force and 0.7 times 0.3 exerted. Number 2, pressure exerted by the water on the bottom face of the container with dimensions 4 meters by 5 meters by 6 meters is filled with water. What is the pressure exerted by the water on the bottom face of the container?
It's pretty much the same thing,
So let's draw a
right?
rectangular container. And it's filled with water.
This would be volume.
Now our goal is to
so-
find the pressure that's exerted by the weight of the water on the bottom surface of the cube. So how can we do that? Well, we know pressure is force over area. And keep in mind, the density of water, if you're wondering, is 1,000 kilograms per cubic meter. Now, the force is the weight of the water, which is mg. And we don't have the mass of the water. However, we know that density, which is rho, is mass over volume. Don't confuse this with pressure. So the mass of the fluid, if we multiply both sides by v, is density times volume. So the pressure of the fluid is going to be the mass, which is density times volume, and then times gravitational acceleration, divided by the area. Now, the volume of, let's say, this rectangular prism is the length times the width times the height. So let me write that down. Sure.
Sorry,
Pressure
guys. I was
that's
paying
exerted by the
attention.
weight
I'll
of
be
water
straight.
on the bottom surface of the cube. So how can we do that? Well, we know pressure is force over area. And keep in mind, the density of water, if you're wondering, is 1,000 kilograms per cubic meter. Now, the force is the weight of the water, which is mg. And we don't have the mass of the water. However, we know that density, which is rho, is mass over volume. Don't confuse this with pressure. So the mass of the fluid, if we multiply both sides by v, is density times volume. So the
Okay.
pressure of the fluid is going to be the mass, which is density times volume, and then times gravitational acceleration, divided by the area. Now, the volume of, let's say, this rectangular prism is the length times the width times the height. So let me write that somewhere.
Right.
Now, the length times the width will give us the area of the bottom surface. Or rather, I'm just going to replace volume with length times width times height. And the area of the bottom surface is just the length times the width.
So pH.
So we can cancel L and W.
Or OHG.
So the pressure that's due to the weight of the water alone is going to be the density of the fluid times the gravitational acceleration times the height of the fluid. So here it is. This is the equation that you want to keep in mind when dealing with the pressure due to a fluid. So we know the density of water is 1,000 kilograms per cubic meter. We have the gravitational acceleration, it's 9.8, and the height of the fluid. Now let's say the first one is the length, the second is the width. So the height, we're going to say it's 6 meters in this example. So it's going to be 1,000 times 9.8 times 6. So the pressure is 58,800 pascals. So that's the pressure due to the weight of the water alone. Number 3. A closed cylindrical container is filled with a fluid that has a specific gravity of 1.7. What is the pressure exerted by the fluid at a depth of 15 meters? So let's say this is the cylindrical container, and it's closed, and it's filled with some fluid. So at a depth of 15, so if you have a fluid, and you want to find the pressure exerted by the fluid alone at a certain depth, this is the equation that you can use. Now we need to know what the density of this fluid is, and we're given a specific gravity. The specific gravity is the density of the substance, in this case the density of fluid, relative to the density of water. So the density of the fluid is going to be the specific gravity times the density of water. So we have a specific gravity of 1.7, and the density of water is 1,000 kilograms per cubic meter. So the density of the fluid is 1700 kilograms per cubic meter. Now we have the gravitational acceleration, and the depth is 15 meters. So it's 1700 times.
That's interesting. So, never mind.
9.8 times 15.
These are good to know.
So the pressure
though.
exerted by this fluid at a point where it's 15 meters deep is 249,900 pascals. And if you divide that by 1,000,
So I'm gonna say for another 20 minutes, so just over 7 hours. I don't know, I feel like I'm good with that stuff. I just want to lock in on heat stuff. These will be nice for later, though. Oh, hey, look.
in this video, we're going to talk about how to solve some basic, simple harmonic motion problems in physics. So let's start with number 1. A horizontal spring with a mass of 0.75 kilograms attached to it is undergoing simple harmonic motion. Calculate the period, frequency, and angular frequency of this oscillator. So if you want to try this problem, feel free to pause the video and work on it. The formula that we need to calculate the period is this equation. It's equal to 2 pi times the square root of the mass divided by the spring constant, which we have all of that in this problem.
So why isn't that on my sheet? Seriously. I have oh, okay. W equals square root of k over m. So that's simple harmonic motion. Okay, so those two up there.
So the mass is 0.75 kilograms, and the spring constant is 300 newtons per meter. So let's go ahead and type that into the calculator. So the period is 0.3142 seconds. So that's how you find the period of a simple harmonic oscillator. All you need is the mass and the spring constant. Now part B, what is the frequency? Frequency is 1 divided by the period. So it's 1 divided by 0.3142 seconds. So the frequency in this problem is 3.183 hertz.
Angular frequency is
Now let's move on to part C. Calculate the angular frequency.
x.
The angular frequency represented by the symbol omega is 2 pi times frequency.
2 pi.
So that's going to be 2 pi times 3.183 hertz. And so that's going to be about 20 radians per second. And that's it for this problem. Number 2. A force of 500 newtons is used to stretch a spring with a 0.5 kilogram mass attached to it by 0.35 meters. What is the value of the spring constant? And calculate the frequency of the oscillator. So let's say this is a wall, and we have a spring attached to it. And there's a mass. Now we're going to stretch the spring using force. And so this is a 0.5
meters.
kilogram mass. And at this point, we're applying a force of 500 newtons to stretch it by 0.35 meters. So how can we calculate the spring constant? Well, we know that the force is equal to kx based on Hooke's law. So the spring constant k is the ratio between the applied force and the amount that the length of the spring changes. So it's going to be 500 newtons divided by 0.35 meters. And so that's going to be 1428.6 newtons.
And we know
So
that
the
the frequency is W over 2 pi.
Now let's calculate the frequency of the oscillator. The frequency of this spring is going to be 1 over 2 pi times the square root of k over m. So it's 1 over 2 pi times the square root of the spring constant, which is 1428.6 divided by the mass of 0.5.
So interesting. So W over 2 pi is equal to F for me. And W equals square root of Km. So, yes, 1 over 2 pi square root of Km is accurate. Square root of K over M over 2 pi.
So the frequency is 8.51 hertz. And so that's the answer.
Okay, I'm just trying to get used to
Number 3.
how to move around these equations.
Per meter vibrates at 25 hertz. What is the frequency of vibration of a spring with a constant of 400 newtons per meter? So what happens to the frequency if we increase the spring constant? As the spring constant increases, the frequency increases. And we know that the frequency of a spring is 1 over 2 pi times the square root of k over m. So notice that the frequency is proportional to the square root of k. And in this example, the spring constant increases from 100 to 400, so it increases by a factor of 4. And the square root of 4 is 2. So therefore, the frequency should increase by a factor of 2. So the answer is 50 hertz. Now, if you want a formula for this type of problem, here's how you could derive it.
Okay.
Since we're dealing with two frequencies, let's write a
Makes
ratio
sense.
for n divided by f1 is equal to the square root of k2. And that corresponds correspond to 400. 25 is equal to just 50. Now let's work on this problem. A 0.75 kilogram mass vibrates according to the equation x is equal to 0.65 cosine 7.35 t. Determine the amplitude, frequency, period, and the spring constant. So x represents the position of the oscillator. So let's say the oscillator is at equilibrium. It's right here. So right now the position is x equals 0. It can oscillate this way and that way. So here x could be 1, and here x could be negative 1. It could be 2, it could be 3, it can vary. The amplitude is the maximum displacement.
So
for the spring.
0.65, right?
If the most that the spring will stretch to is up to this line, and let's say that's 1.5. And so the most that it can stretch to in the other direction will be here. So in this case, the amplitude, the maximum x value, is 1.5. Now x could be anywhere between negative 1.5 and positive 1.5. So x represents the current displacement. A, the amplitude, is the maximum displacement. So make sure you understand the difference between the two. Now, you need to know the generic form of that formula. The current displacement is equal to the maximum displacement times cosine omega t. Now sometimes we may have a phase angle, but we don't have it for this problem, so all we have is this one. So the amplitude is whatever number you see in front of cosine. So the maximum displacement is 0.65, which means that x can be anywhere between negative 0.65 and positive 0.65. So if you graph this cosine equation, the amplitude is 0.65 and negative 0.65 on the graph. And cosine starts at the top. So the cosine wave is going to look something like this. And it's going to keep oscillating between these 2 points. Now, what does this number represent? 7.35. Notice that the variable in front of t is omega. So the 7.35 represents the angular frequency of this oscillator. So 7.35 radians per second. And if we know the angular frequency, we can now find the frequency. The angular frequency is equal to 2 pi f. And so 7.35 radians per second is equal to 2 pi times the frequency. So the regular frequency is just 7.35 divided by 2 pi. And so you should get 1.17 hertz. Now how can we calculate the period? If you know the frequency, then you know the period. The period is simply 1 over the frequency. So in this example, it's 1.17 hertz. It's 1 over 1.17 hertz. So 1 over 1.17, that's 0.855 seconds. So we have the amplitude, we have the frequency, and we have the period. So the last thing we need to calculate is the spring constant. So what formula can help us to do that? Well, we know that frequency is 1 over 2 pi times the square root of k over m. So the first thing I'm going to do is multiply both sides by 2 pi. So I can get rid of this. So on the left I have 2 pi f, and that's equal to the square root of k over m. I'm going to take the square of both sides to get rid of the value on the right. So I have 2 pi f squared, and when you combine a square and a square root, those two will cancel. So on the right all I have is k over m. So I'm going to multiply both sides by m. So let's get rid of that.
Okay.
Use that equation. So the spring kilograms.
I think I'm pretty comfortable with that now. I'm glad that I got figured out. I'll probably want to do that eventually. Probably a simple pendulum one. But I do want to do some heat.
Let's work on this problem. Calculate the change in the internal energy of a system if 300 joules of heat energy is added to it, and if the system performs 200 joules of work. Now, to get the answer, we need to use this formula. Delta U, which represents the change in the internal energy of the system, is equal to Q, which represents the heat energy flowing into or out of the system, minus W, the work performed by the system. Now, this equation is associated with the first law of thermodynamics, which basically is the principle of the conservation of energy. So in thermodynamics, there's two ways in which you can change the internal energy of a system. You can do work on a system, or the system can do work on the surroundings.
I think I'm actually pretty good with this stuff, actually.
In this video, I want to talk about the second law of thermodynamics as it relates to heat energy and entropy. So let's say if we have a metal rod placed between a hot object and a cold object. Heat will naturally flow from hot to cold. That's a simple natural process. It's spontaneous. It occurs on its own. Heat doesn't naturally flow from cold to hot. It just doesn't happen. The only way for you to make it happen is if you were to pump energy into the system. So, for example, a refrigerator will take out heat energy from inside the fridge and pump it outside of it. And that's how a refrigerator can cool the stuff on the inside. But it takes energy to do that. It doesn't happen naturally. A good way to illustrate this is, imagine if, let's say if you have a ball on top of the hill. The ball will naturally flow in a downward direction, the same way as heat flows from hot to cold. Heat flows from a high temperature, naturally, to a low temperature. And this ball is going to flow from a high position to a low position. Now, if you place the ball at a low position, it won't naturally go towards a high position. It just doesn't happen. The only way for you to make it happen is you got to put energy into it to get it over that hill. And the same is true for heat. Heat doesn't flow naturally from cold to hot. Now, you could make it happen. You can pump heat to warm up a certain environment. Heat pumps do that. However, it costs energy to do so. Now, as heat flows from hot to cold, this is a spontaneous process. And for a spontaneous process, the entropy increases. It's going to be greater than zero. And that's another statement of the second law of thermodynamics. For natural processes, the change in entropy will be greater than zero. Now, if you have an ideal reversible process, at best, the entropy can be equal to 0. However, most systems do not behave perfectly, so a natural spontaneous process will tend to lead to higher disorder. So for natural processes, the change in entropy is positive, it's greater than 0. And so that's the basic idea behind the second law of thermodynamics as it relates to entropy. Natural systems tend to go towards disorder. So for example, let's say if you take your room, it takes energy and effort to clean your room. Naturally, your room will tend to get messy and dirty and things like that, but it takes effort to clean it. Even if you were to leave it alone, things will get old, houses worn down. Let's say if you leave your car out in the open for 10 years, it's not going to become newer, it just gets worse. And so natural systems, they tend to go towards a state of disorder rather than a state of order. For example, let's say if you drop a glass cup, it's going to break to pieces. Now those broken pieces are not going to naturally just fix themselves together, it doesn't happen. So it's very difficult to take something in a disorderly state and turn it into an orderly state. It takes energy to do that. Naturally, things tend to go towards a disorderly state. And so for a natural spontaneous process, the entropy of a system tends to increase. And that's the general idea behind the second law of thermodynamics.
Should I call it wraps at 7 hours? Call it a day here. Feeling pretty good, I think. Alright, gang. Well, it has been quite fun. We've studied for approximately 7 hours, maybe a little less than, but that's okay. There's only 24 hours a day, and you sleep for 8 of those, so you're only awake for 16. You gotta eat for 3 of those. That's 13 available hours, and I studied for half of those. Over. I still got time tomorrow. Oops. Oh man.
This video is for those of you who want to
I wanted to stop it right on time.
Now for
Alright. I mean, yeah, this is the next recommended video. That's about the level I'm at, huh? Yeah, thanks, bro. Alright. Chat, I will see you later. I am hungry.